Hey everyone, this is the second video going through some trial exam questions. Hopefully this one's not going to be as long as the other one. I know it's tedious, but we've just got to get through it. Alright, so question number 3. So this is from the Heffernan 2022 exam 2. So a trial exam. Alright, so what f of x equals 1 minus x times e to the power of 2x plus 1. Part of the graph is shown below. State the maximal domain and range of f. Alright, from the graph it doesn't appear that there's any restrictions on x, any horizontal asymptotes, etc. And we can see it's also a composite function, so you could think of it as a composite function if you like, but your domain is basically any real value, so we're going to go from negative infinity to infinity. Just make sure you use curved brackets when you're working with infinity. Alright, for your range, I can see here that we've got a maximum point here, so we might actually just do that on the calculator. Just move you over here. Alright, so we want to calculate, sometimes I always go to the wrong one. Alright, the function max. Come on. Alright, and put the expression in. So 1 minus x times e to the power of 2x plus 1. And just make sure everything's correct. Alright, so your maximum value is 1.5, so this point here is 1.5, and it is included, so I'm just going to put that here. So remember, you've got to put your minimum value first and then your maximum. Now if we just change that around to be our minimum, and just so I don't have to write this again, I'm just going to copy it first. Alright, and then go back in calculation and then just do my minimum just to make sure there's nothing. Should be infinity. Alright, so our minimum value is negative infinity. Make sure you use curved brackets, and the maximum is 1.5. Find the values of x for which f is strictly increasing. So we can see from the graph it is increasing until we get to 1.5, not including 1.5 because that is where it is 0. So x is an element of, so we're going from negative infinity to 1. Oh, sorry, not 1.5, my bad. We got the x value before, negative 0.5. Sorry, I was writing the y value, we want the x value. So we did get that, come on. We did get that before when we did the maximum value was 1.5. It gave us the corresponding x value, so negative 0.5. And that needs to be a curved bracket too. Alright, the function f undergoes a transformation to become the function g, where g of x equals negative. Alright, so we've had a reflection and x minus 0.5, and we've had a translation. Write a sequence of 2 transformations that map the graph of f onto the graph of g. Alright, so first of all, that negative means we've had a reflection. Sorry, I'm going to write reflected. Reflected, and we're changing our y value, so it's reflected in the x-axis. And then that minus 0.5 means we've had a translated to the right 0.5 units. Alright, now because it's been a reflection in the x-axis and then a horizontal translation, the order does not matter. So you could have the reverse of that if you wanted to, so the translation and then the reflection. Show that the graph of G has a stationary point at 0, negative 1.5. All right, so anytime we see a stationary point, we want to do the derivative. So dy dx, and we can just do that on the calculator. All right, so just trying to remember which function to use. All right, so d dx, and I can just highlight this and drag it down. And I'm going to go back and put it into standard mode. So negative 2x. 2x plus 1 minus e 2x plus 1. Just double check that I've written it down correctly. Alright, and then we're going to let that equal 0. Now it is a show that question, so we'll talk about how much we need to show in a sec. Alright. Oh, I was wondering, I did it wrong, didn't I? I was like, we already had the stationary point. Maybe there was another stationary point that we didn't know about. Alright, this is where you need to read the question properly. Alright, so we had G. Alright, so remember G had changed. Alright, and this is where you could use define. So I might actually show you, because I haven't used define yet. I used to be a huge fan of define, but sometimes I just thought it wasted time. Like then. No, I don't want two defines. Oh no, I don't want a defy. Alright, define f. Alright, and I can just drag this down. I don't have to write it again. No, that's not what I wanted. Alright, so told the calculator, can you remember that for me? And it's saying, yes, no worries. Alright, so we can do those transformations straight onto the calculator. So we've got negative f of x minus 0.5. Alright, just make sure we've put that in correctly. Negative fx minus 0.5, good. Alright, now I don't really have to write that down properly. What have we got? Oh, yes, we do. Alright, so I'm going to write g of x. I'm just thinking you could probably just do transformations, to be honest, because this is a really pain in the butt thing to write. I'm going to use decimals because there's decimals in the question. E to the 2 x minus 0.5 plus 1 minus 1. So g dash x. Yeah, the more I do this, I'm thinking just show using mapping. So time consuming, yeah, thank you. Because it doesn't, if it said to find it, this would be alright, but I have to write everything down as we go because it's a show that question. 2x e to the power of 2 x minus 0.5 plus 1. Alright, and then we can let that equal 0. So that means x is equal to 0 using your null factor law. And e, yeah, so I'm going to highlight it. So your null factor law means that this is either equal to 0 or the x, or this is equal to 0. Now your e cannot equal 0. E to the power of something cannot equal 0. So that means x has to equal 0. And then g of 0, I'm just going to be cheeky and put that in. Now, if we use mapping, and I'm curious to now know what they did on their solutions. All right, so we've got negative, and I've already written it incorrectly, so I'm just writing the stationary point for the initial function. So negative 0.5, negative 1.5. Now, using mapping, we're going to have a reflection in the x-axis, so we're going to multiply that by negative 1, and then it's shifted to the right 0.5 units. Sorry, so plus. All right, so that's going to give us 0, sorry, and positive 1.5. Oh, and I got a negative. How did I get an? Oh, because it is it's positive. Sorry. Sorry, it should be a positive. I wrote the wrong coordinate. All right, so just down here, it is a positive. Is a positive 1.5, and I wrote negative. All right. So you could, yeah, mapping worth 1 mark. I don't know. It's a show that question, so I kind of feel like doing the mapping is not enough, but maybe it is. Let's have a look at what the solutions were. Oh yeah, so they used the mapping, so method 1, and we did it algebraically. All right. Whoops. Sorry. All right, now let's move on to an inside exam, so a different exam. So we're looking at exam 1, question 5. All right, so we've got f from 0 to infinity. So f of x equals e to the x minus 1, and I can see it's a trapezium question. Trapezium, estimating the area using trapeziums is new to the course, so you will expect it to be on there. So this is an exam 1 type question. You could get an exam 2 question as well, or either, don't know. We have no idea what is on the exam. All right, so 2 trapeziums of equal widths are used to approximate the area between the graph with the equation y equals f of x and the x-axis between the lines with the equations x equals 1 and x equals 3. The heights of the left and right edges of each trapeziums are the values of y equals f of x as shown in the graph below. Find the total area of the trapeziums. So the area formula is on your formula sheet. All right, so just have to quickly find it. So here it is, trapezium rule approximation. That would be useful in a exam 2 type question. I feel like I've seen it as a multiple choice exam. So this is the xn minus x0. That's just your end x value and your starting x value over 2 times the number of trapezium. Sorry, n is your number of trapeziums. So yeah, you'll see a multiple choice question, I think, that uses that. But let's just use the area of a trapezium because I find it just so much easier for questions like this. So the area of a trapezium, even though we can't use a, what am I talking about? We can't use our bound book. You should know the formula for trapezium off by heart. All right, so for your trapezium formula, your A and B are your parallel sides. So I might just draw a trapezium here. So this is your A and the B, it doesn't matter because you're adding them together and your height of your trapezium. So here, our height is that distance there, so it's 1 in this case, and then this is your A and this is your B. So it doesn't matter about the H because it's 1. So let's do the first trapezium. So half times, so all we need to do is substitute that value of x in. Now my little formula's stuffed up because I scrolled too quickly. Alright, so half. Alright, I need that function again. Where is it? I'm just going to write it here. Alright, so the first one, so e to the power of 1 minus 1 plus b, e to the power of 2 minus 1. Right, so there's the area of the first trapezium, and then the area of the second trapezium, e to the power of 2 minus 1 plus e to the power of 3 minus 1. And we just now have to tidy things up. So we look for common factors. So the half is common to both. All right, we've got a minus, let's just open that up. We've got e to the power of 1 plus e to the power of 2 minus 2. Sorry, don't want that bracket there. Plus e to the power of 2 plus e to the power of 3 minus 3. All right, we've only got one e, or e to the power of 1. Doesn't matter if you leave it as that. We've got 2 e squared, and we've got 1 e cubed minus, and I don't know why I wrote 3 there because it should have just been 2. So let's just fix that up, and that should be a 4. Sorry, my bad. Let's just quickly tidy that up. So that should be a 2, and this should be a 4. Now, you could then take out, oh no, you can't take it out. E is a common factor. So we just got to leave it like that because E is an exact value and it's exam 1, so we can't do any more than that, basically. I'm just thinking if we were using the formula, let's just get the formula up. See if I can snip it. Because I don't want you to get stuck in your Alright, sorry, I just realized it was going to take forever, so I just paused it. I don't want you to be stuck in your exam because you don't know how to use the formula. So n is how many trapeziums we have. So n is equal to 2. So our xn, so x2, our end, our second x, alright, alright, so xn, our end value, which is 3, so I'm just substituting it into this formula, minus x0, your starting value, which is 1, over 2 times n, which is 2 times 2. And you'll see that becomes 2/4, which is where your half comes from. Alright, so we're going to put that at the front. So area equals a half. And then all this stuff inside is basically what we've just done. So f of x0, your first value, is e to the -1. Then your next value is 2 times e to the -1. And then your next value is 3 e to the -1. Sorry. Why did I put a 3 there? It's not 3. It's just... Alright, so your first value is this. And just take notice, your last value is just that. This is what I just did incorrectly. Each value in between is multiplied by 2. So you can see there's your 2. So just be careful your 2 end values only get counted once. See why I think it's easier just to use the trapezium formula. Half. Alright, so we've got e minus 1 plus 2e minus 1 plus e minus 1. And then you'll get the same thing. So bringing all your like terms together. So we've got e plus 2... Oh. Sorry, I think I forgot my squareds. I did. Sorry, that should be a squared. should be a 3. Oh my gosh. See, 3 minus, and that should be a 2, sorry, minus 4. All right, so trapezium formula, half times a plus b times h. All right, there's your formula sheet formula. I think a lot more difficult to use, but if you do get stuck, that's how you use it. You also need to be aware it could be a multiple choice question where you need to understand what the xn, x0, etc. all mean, and that this starting value and your end value only get counted once and everything else gets counted twice. So when we did this in class, I kind of explained that, but if you want to go through it again, more than happy to. All right, let's move on. All right, so we've got g of x equals m minus e to the power of x. The graphs of y equals f of x and y equals g of x intersect when x equals k. Show that k equals, okay, so we've got, all right, let's just write down y. Oh. Okay, so that was our e to x minus 1. And g of x is m minus e to the x. All right, so let's just let them equal each other. All right. So we've got 2ex equals m plus 1. E dx equals m plus 1 over 2. And then x equals log base e m plus 1 over 2. All right, sometimes show that questions, and why did I have k? Oh, therefore. Show that question so you can use your answer later on, sometimes. All right, part C, the graph of the functions f of x and g of x is shown in the diagram below, so you can also see where they intersect, so that's your k. The area of the shaded region which is bounded by the graphs of f and g and the y-axis is that. Find the values of m and k. All right, so setting up our definite integral, we're going from 0 to k, when k was defined, calculated before, but in terms of m, so we're going to just leave it like that for now. All right, f of x, no, sorry, g of x is on top, minus f of x is on the bottom, dx, don't forget your dx. So let's just put everything in. And I might need more space in this, so I might go over to the left a bit more. Alright, k, 0, g of x, what was g of x? M minus e, it's nice that they wrote it again for me. M minus e to the x minus, and put it in brackets because you got multiple terms there. Okay, let's find the antiderivative. So m becomes mx, negative 2ex just stays negative 2ex, and then 1 becomes x k0. Alright, substituting in k, we get mk minus 2ek plus k, minus, substituting in 0. So e to the power of 0 is 1, so we're going to have minus negative 2. So mk minus 2ek plus k plus 2. Alright, so that's as far as we can go with our definite integral. So in the question, it tells us that that is equal to 6 log base e 3 minus 4, and the question actually asks to find the values of m and k. So let's make that equal whatever it was. Is it 6 log base e of 3 minus 4. Now do recall that k, what we had earlier, log base e m plus 1. Now I've forgotten it already. M plus 1 over 2. Alright, so we're going to substitute that in. So we're going to have m log base e m plus 1 over 2. So everywhere we see k, we're just going to substitute in that log, minus 2e, this is annoying, log base e m plus 1 over 2 plus k, so we're going to just log e m plus 1 over 2 plus 2. Let's just make that equal 6 log base e of 3 minus 4. Alright, so let's just see what we can do here. So these will cancel each other out. I don't know what else we can do. Okay, we've got logs, same logs, so we can use our log laws to bring them together. So I'm just going to move that m to the power here. Oops. Alright, so we're going to have log base e of m plus 1 over 2 to the power of m. And then I'm just going to skip this middle term and put our other log next to it. M plus 1 over 2. Oh, I could have brought that out as a common factor. Let's just leave it there for now. Oh, now I'm thinking I should have had a common factor. Alright, I'm going to change that. Right, change. So we're going to have log base e as a common factor times m plus 1. Alright, so that's going to get rid of my log. Oh, well, not get rid of them, but I've dealt with them. Alright, and then we've got this minus 2 times m plus 1 over 2, and then we've got a plus 2 here. Alright, just tidying things up a little bit. Alright, so that 2 and that 2 cancel out. So we've got minus m plus 1. Hold on. Minus, so that plus 1 should become a negative 1. Plus 2 on the end is equal to 6 log e3 minus 4. Okay, so let's just try to make the left side kind of look like the right hand side. Oh, we've got to solve for m basically. Don't know why that just happened. I just want to erase, guys. Oh, right, just ignore that. I have no idea why it did that. I think my computer's also kind of crapping itself. Alright, so negative 1 plus 2 is 1. So let's just keep the log here. Oops, 6 log e. Oh, I forgot that minus m. Yeah, my computer's not feeling very well. I can feel it heating up. It's like my brain. Alright, so we've got this m. So we'll keep that m there. Alright, so I'm going to bring that 1 over, so it's a plus 1, so minus 1, so minus 5. Alright, so now we're just going to have to equate the position of things in our equation. So we've got an m here and a 5 here. So let's just say m is equal to 5. So if I substitute m equals 5 in, then my left-hand side should equal my right-hand side. So I've got 6 here. So here's my multiplier. So 5 plus 1 gives me 6. Awesome. And then if I put 5 into here, we get 3. So that's good. All right, so m is equal to 5. What I could have also done, yeah, that's probably a pain in the butt way of doing it. All right, I think just equating those parts of your equation is the best way to go. All right, so m is equal to 5, so that means k is equal to log base e m plus 1, which was 6 over 2. So that is equal to log base e of 3. All right, so m is equal to 5 and k is equal to log base e of 3.